Hello, welcome back to our little corner on the web, where we hope to develop and nurture a love for math. Today, we'll go over questions from the 26 PMO qualifying stage. Thank you again for the organizers for freebie sharing the questions. We'll go over question 7 in part 3, or the second to the last problem of the set today. So here I'm flashing the problems first. The question 7 states or asks, let p of x be a polynomial of degree 3 satisfying p of 2 is equal to 6 and p of 6 equal to 2. And p of 1 is also equal to p of a. There exists positive integers a different from 2 and 6 and b such that p of a equal to b and for any p satisfying these conditions. What is a plus b? Okay. For those of you who want to try first, you can pause here and give the questions a try. Okay, so let's dive in. So the real question here, I guess, and also for me when I was first trying it, was how do we begin, right? So I can tell you how I first started and then what the twists and turns I sort of had to go through. I first tried, let p of x be equal to some, alpha x cubed plus beta x squared plus gamma x plus some other constant, right? And I tried this. I tried plugging in p of 2 here, equated that to 6. I tried plugging in p of 6, equated that to 2. And also did p of 1 equal p of 8. Didn't really get anywhere meaningful, at least at first try. It might still be possible. I don't know. Halfway through it got a little bit too messy. And I tried to so I decided to abandon it. So I said, what else do we do with questions where we're given, p of something equals a constant? And so the other thing that came to mind was to try using remainder theorem. Okay, so usually when we're given a remainder theorem, we're given something equal to 0, but here we're given something equal to a constant. So first, I said, well, then p of 2 can be written as x minus 2 times some other, polynomial of second degree, a of x, plus 6. And also, here, when you plug in 2, this thing here goes to 0, and then we only end up with 6. Same manner, p of 6 can be written as x minus 6 times some other, quadratic plus 2, right? But note that we can also combine these, right, to be some p of x equals a constant times x minus 2, x minus 6, and some other x minus some other root plus some remainder, okay, some r of x. Okay, so note that since we already know these two, we can divide the whole thing by x minus 2, x minus 6, and we should be left with a constant. When we're dividing with a quadratic, we know that the remainder has to be some linear expression. So here, we know that if x equals 6, right, our remainder should be of the form, I'm just going to use a here, even though it's used somewhere else, ax plus b. The remainder should be of this form, okay? When x equals to 6, the remainder is some 6a plus b, and that's equal to 2. When x is equals to 2, the remainder will be some 2a plus b, which is equal to 6. Okay, so we can solve for a and b here, actually. So now, when we subtract the second equation from the first equation, we get 4a equals -4 or A equals -1. Again, these A's and B's are different than the A's and B's here, okay? It's just to solve for what this R of X really looks like. Okay. So since A is equals to -1, we can plug it in, whether the first or second equation doesn't matter. Plugging it into the second equation, we get -2 plus B equals 6, or B is equals to A. So now we can rewrite P of X. So now P of X is some K times X minus R, the thus far unknown root, okay? X minus 2, X minus 6, plus the R of X, which is AX plus B, but we know both A and B now. Oh, why did I write that there? Wait, let me correct this. This is B equals A, sorry. Okay, so putting it all together, we basically have 8 minus X as the form of the remainder. Okay, when we're dividing by that quadratic, X minus 2, X minus 6. Okay, so now we have that. So the next question actually that comes is, what can we do next? First we can create some space here. But what can we do next to get us sort of further along, right? So the thing that we haven't used in the problem is actually P of 1 equals to P of 8. So let's sort of try what that looks like and what insight that can give to us, because the rest of the things in the problem we actually already have used. Okay. So P of 1, if we just plug it in here, is equal to some constant times X minus R times -1, okay, times -5 plus 7. Okay. And again, this is equals to P of 8. So let's solve for P of 8. P of 8 is K times this X minus R, okay, times 6 times 2. Okay, and there's no remainder. Okay, P of 8 equals 0. Or R of 8 equals 0. Okay, so now let's equate those two and let's see where we end up. Okay, for now we actually don't need the first 3 rows there, so I'll delete them for now. We've used all the information we can gather from those. Okay, just so that we have some space. Okay, so let's equate both sides. So the P of 1 just becomes 5K times X minus R plus 7. And that's equal to 12K X minus R. Oh, oops, I didn't substitute it in. This X is a 1. Sorry about that. That's why I'm copying the wrong things also. And this X here is an 8. Okay. This one and this one are also. If you were in a classroom, some kids would probably already be shouting at me. So this is 1. This is 8. Okay. So expanding, and we'll try to find a relationship between K and R. So the first one, or the left-hand side, becomes 5K minus 5KR plus 7. Okay, is equals to 96K minus 12KR. So doing some transpositions, we have 7KR plus 7 equals 91K. Okay, and dividing the whole thing by 7, we end up with KR plus 1 equals 13k. Just writing it slightly cleaner, 1 equals 13k minus kr. Or I'm going to write it here in the upper right because we will use it in a bit. K can be written simply as 1 all over 13 minus r. Okay. So now we can actually rewrite the polynomial I wrote there in green. Okay, we don't need a P1, P8 anymore. We can rewrite this polynomial in green as getting rid of k. P of x is x minus r divided by 13 minus r, replacing k, times x minus 2, x minus 6, plus 8 minus x. Okay. Note that we're looking for positive integer solutions A, meaning when we plug in A, we should get another different integer B, right? That satisfies this equation. That satisfies that when we plug in A, we get B, and we plug in B, we get A. Well, to get an integer here, the first term here, this, has to be an integer. And it's only an integer, or at least, well, not only, but one of the most obvious ways for it to be an integer is x equals 13, since we don't know what r is yet. Okay. So again, plugging in now x equals 13, let's see what integer we can get back. And then we can sort of verify if we can find an r that satisfies that integer, giving back the original, right? Meaning 13. Okay. So when we plug in 13, okay, P of 13, oops, I'm not a fan of. Okay, so when we plug in P of 13, we get 13 minus r over 13 minus r, so that's 1. Okay, 1 times 11, okay, times 7 plus 5. Okay, so we get, oh, sorry, minus 5, not plus 5. Minus 5. So we get 77 minus 5, or 72. Okay. So we need to make sure that this actually works. So we can plug in and see what we can find for P of 72. Some of you might just stop and say, well, I found 13, so it must be 13 plus 72. And hence the answer is 85. You would be correct. But for the purposes of completeness, let's plug in what P of 72 might look like and if there's an R that actually satisfies. Okay. So P of 72 will look like, will be equal to 72 minus R all over 13 minus R times 70 times 66 minus 64. Okay. So if this is equal to 13, we can solve for R. Okay. So let's rewrite this as 72 minus R times 13 minus R times 7 times 10 times 6 times 11 minus 64. So for this to become 13, the first term here has to be 77. But we already have a 77 between these two. 7 times 11. So that means that 72 minus r over 13 minus r must cancel the 10 times 6. So this must be equal to 1 over 60. Okay, so solving for that, we have 4,320, which is 72 times 60, minus 60r is equal to 13 minus r. Okay, or 4,307 is equal to 59r, and hence r is equal to 73. Okay, if you go divide 4,307 by 59. So actually, we've found r now. So just for completeness, we can write p of x. So p of x is actually x minus 73, okay, all over 13 minus 73, or negative 60. So that's actually our constant, times x minus 2 times x minus 6 plus 8 minus x. So we found p of x, so therefore we know that the two different positive integers that can swap, just like 2 and 6, is actually 72 and 13. Okay, so yes, the answer is indeed 13 plus 72 equals 85. Hope you found this solution helpful and educational. If you did, do hit the like button and subscribe. Thank you for watching.